Hello, and welcome to Unit 5 Crash Course, an interesting lesson over electromagnetics, quantum mechanics, and periodic trends.
You were late.
Okay, I'm sorry, Elena, but I can't move at the speed of light.
Fun fact, light travels at the speed of 18 billion meters per minute, which is the speed Plus would have to travel to circumnavigate the Earth 7.5 times in 1 second.
Light is interesting because it doesn't travel to our eyes in a straight line. Light travels in waves, which is characterized by its wavelength. The shorter the wavelength, the higher the frequency. The longer the wavelength, the lower the frequency.
The light we're able to see is in the middle of a list of waves with varying sizes, the electromagnetic spectrum.
Yes, a spectrum that starts with radio waves, with an average size of 10 to the 6 meters, and gamma rays, with an average size of 10 to the negative 16th meters.
Yes, and as I said before, visible light is in the middle of that spectrum with a maximum wavelength of 700 nanometers and a minimum wavelength of 300 nanometers. Within that 400 nanometer section of the electromagnetic spectrum, all the colors of our rainbow are visible.
Now that we've thoroughly explained electromagnetics, it's time to move on to a rather sexy-looking man, Niels Bohr. And by sexy-looking, I mean in comparison to Amadeo Avogadro. Yeesh.
Ooh, you're right. Although, Avogadro's really smart. Adrian, I've got his number. You want it?
No thank you. He's all yours.
Anyway, Bohr. He came up with a model for how electrons behave around a nucleus. This model had the electrons traveling around a nucleus on fixed distance, circular orbitals. Unfortunately for him, this was incorrect.
Now enter Erwin Schrödinger, the man who walked up to Mr. Bohr and said, "Electrons do not travel in circular fixed path. It's much more complicated than that." He proved himself right by doing a bunch of complicated math and came up with the new electron model, the quantum mechanical one.
Now this is where things can get a little tricky. In the new quantum mechanical model, the way of expressing an element's electrons takes this form. In this notation, I guess, N stands for the principal shell, or the level in which the subshell is currently in. X stands for the specific subshell, and E stands for the amount of electrons that are actually in the current subshell.
You just heard Adrian say the word subshell quite a bit, so what is a subshell? A subshell is a specific shape of an electron orbit that an electron can take, depending on where it's located. The first subshell, labeled S, takes the shape of a sphere, can be found in groups 1 and 2 of the periodic table, and can hold a maximum of 2 electrons per principal shell. The second subshell, labeled P, takes the shape of a dumbbell, can be found in groups 13 through 18 on the periodic table, and can hold a maximum of 6 electrons per principal shell.
The third subshell, labeled D, takes the shape of a clover, or double dumbbell. It can be found between the transition metals and can hold a maximum of 10 electrons per principal shell. The fourth and final subshell, labeled F, takes no specific shape, can be found between the lanthanides and actinides, and it can hold a maximum of 14 electrons per principal shell.
Let's do an example so you can figure out how this works. I've chosen the wonderful element holmium. Shout out to Jordan Folk. This one's a long one, so you can see how the weird rules for D and F subshells work. So what you want to do is you want to start from the very beginning, the top left here, and this here is your first S block, this H and this HE, hydrogen and helium. The helium, you can imagine, is right here. So your first step to do is you're in the S block because you're in the first 2 groups. So you're in the 1S group, but you've got 2 of them, so 1S2. Then you want to go down to the next one. Now you're on 2 S2 because you're on lithium and beryllium. Then you want to go over here. Now you're in the P block. You're in 2P, 1, 2, 3, 4, 5, 6, 2P, 6, and then you just continue 3S2. Then you've got 3B6. Now you've got 4S2, but now you've hit the transition metals, which is weird. You would think this was 4D, but it's actually not. It's 3D for some reason. So this one here is 3D, and you go all the way across 3D 10. Now you've hit the P block again, and then we're back at 4P6. I'm going to go back down here, but it should just go in one line, but we've ran out of space because I'm not smart and I didn't start over here. Okay, now you're over here. Now you're on, what is this, 5? 5, what a weird 5. 5S2, and now you've got to go back, since your last D was 3, you got to do 4D10, and then once you cross that, you're back at 5P6, and you basically just do that again. Now you're at 6S2. Now you've hit the lanthanides. Now you want to do is go and change it to 4F1, 4F2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 4F11. And that is the electron configuration for holmium. Now that you have your electron configuration, you might want to know how many valence electrons your element has. So to do that, you want to find your subshell, which is S, P, D, or F, that has the highest principal shell, which would be the numbers in front of it. The highest principal shell we've gone to is 6. So we've got, you take this, and you go that. You've got 2 valence electrons. Let's say it stopped here, then you would have to go to all of the 5s. And since you have 2 5s, 2, 6, 6 plus 2 equals 8 valence electrons. That's if it stopped there, for an example. I don't know which one that is. 5P6, that's xenon. Xenon has 8 valence electrons because it's a noble gas. The final things you might want to know are something called periodic trends. These happen to be patterns that happen consistently across the periodic table. The first 2 trends, atomic size, which is the distance between an element's valence electrons and its nucleus, and metallic character, which is the ability for an element to act like a metal, both increase by going left and then down. In other words, the elements closer to the bottom left-hand quarter of the periodic table have the biggest atomic size and are more likely to act like a metal than the rest.
The last 2 trends, ionization energy, which is the amount of energy that is required to remove an electron from a gaseous element, and electronegativity, which is how easily it is for a gaseous element to gain electrons, increase from left to right and up the periodic table. This means that the elements that are closest to the top right of the periodic table require the most energy to remove an electron, but are the easiest to gain one.
Thank you for watching our video on electromagnetics and quantum mechanics.
Hopefully you learned a lot and enjoyed the debauchery. Do you know how hard it is to write chemistry jokes? Nitrogen, oxygen, potassium.
If you found this video a tad cringy, I'm sorry. It looked a lot better on paper. You might not ever see us again. Physics is probably going to kill us all.
That's all, folks!